Okay, good morning again. I am going to present on behalf of Tiago Oliveira. The work is entitled Cohesive Zone Analysis of Torsional Tubular Joints with a structural adhesive, and this work was also under the supervision of Professor Campilho, and it was developed in ICEP and in AG in Porto, Portugal. This is the main outline of the work: objectives, introduction, joint geometry, materials, numerical settings, validation, development, conclusions, and future work. Okay, in this work we are going to study, or we studied tubular joints again, but in this case under torsional loads, and we performed that numerically, and we validate numerical technique using experimental work. Okay. Here we have the joint geometry, tubular lap joint. However, in our case, we are changing the substrate thickness from 1 to 5 millimeters, and the joints are under a torsion load, which is quite common for power transfer in this case. The substrates are made of aluminum, the series is 6000, and adhesives. Again, we tested 3 different adhesive systems: AB138, R.D.G 2015, and Zika 47752. All of them have been previously characterized. For the numerical model, we are using again abacus and cohesive zone modeling, but in this case, in contrast to the previous presentation, in this case is a 3D model. Okay, in this case, we have a representation of the model with the mesh. We use different mesh sizes according to the position in the geometry. For example, this is the lap area, and the mesh is much refined, and in the ends where we don't need too much detail, the mesh is bigger to save computational resources. Similarly, here we show the kind of the radial sweep of the mesh, and we calculate the stresses. The torsion analysis was done with 3D, but the stress distributions were obtained similar as before using a axisymmetric model because it's quicker to run. So in this case, we are presenting the R.D.G 2015 with an exterior substrate of 1 millimeter and an overlap the 20 millimeters, which is the common representation. Here we are comparing again the numerical technique against the CCM, against the numerical against experimental, sorry. And here we can see that we have a good, more or less good match for the AB138. 2015 has a good match. AB7752, it has a good match, however, under predicts, but it is expected because of the cohesive law, as it has been reported in literature before. Here we continue with the stress distributions in the R.D.G 2015, which is the adhesive I will continue presenting through the presentation. We can see that we have a reduction in the stresses along the overlap as we increase the substrate thickness, which is expected. This is for the interior pipe, and this is for the exterior pipe. The exterior pipe doesn't have that much influence as the interior pipe, perhaps because let's say that way, the bond line is still more or less in the same position. Okay, here we compare the P delta curves numerical by changing the inner pipe, the inner pipe and the outer pipe. As I say before, we can see that only for the thin substrate there is a difference. Later on, the external tube or external pipe doesn't have any effect. However, for the inner pipe, we can see that the thicker substrate or thicker inner pipe has the largest advantage. Here again, we compare the joint strength for 20 and 40 millimeters, varying inner pipe and external pipe. And we can see again, the inner pipe has more effect, and the R.D.S.G 2015 seems to be the most suitable adhesive for this application. In conclusion, we have a good agreement between experimental and numerical results with a difference around 6.1%. The shear stresses change between the overlaps as we expect. Usually, brittle adhesives work better with shorter laps, and ductile adhesives work better with longer. It's a known fact. We found that the inner tube thickness has more effect than the external tube. However, we cannot use external tubes higher than 2 millimeters because even though it doesn't have an effect, it starts yielding. So that's the problem. For my part, it will be all. Any question?